Hi everyone. All right, so today's lesson you can see is going to involve some equipment that I snagged from the classroom a week ago. I did want to show you something for fun though. Trying to keep my sanity. I've got these for advisory, these little ping pong nets. I did across my dining room table. It's kind of working, keeping my sanity a little bit. All right, anyway though, if you guys recall, we started learning about sound waves, and what we did last week is we determined the speed of sound. It does vary depending upon the medium, the material that you're in, but in air at room temperature, it's approximately 340 meters per second. So we've got that down, but then we know there's other things about waves in general. There's things like frequency, wavelength period, amplitude, all of that stuff. So we're going to focus on one of them in particular today. I'm not going to say it now, but you should have a really good idea of what it is when I'm, of course, finished with this, okay? All right, so first things first, if you guys didn't know, these are tuning forks. Mainly, they were meant kind of in the old days to tune a piano. So if you play an instrument or sing, I think you're really going to like the connections that we start to draw with waves and how it relates to sound. So if I just grab one of these randomly, I showed you guys in the PowerPoint the other week that a tuning fork can create a sound wave by basically swinging back and forth because then it compresses the air right here, and compression of air creates these pressure differences, which is a longitudinal wave, and it is a sound wave. All right. You can see on the side that it has certain numbers. I'll get into that. And if you do know music, it actually has keys, like this is the key of F, and there's a musical scale. Okay. Anyway, though, when you do use these in the classroom, you want to hit them against something rubber and not too hard, just because they can actually kind of break the structure they're supposed to have, which then makes them swing differently. But anyway, if you hit this, bringing it close to the microphone, you guys should have heard a certain note, hopefully. Okay, let me grab a different one now. Let's go to this one. Is now different in terms of its length. All right, so if you think about it, before I even hit it, this goes back to our pendulum activity when we started this whole idea. Simple harmonic motion with the pendulum's period that it would swing back and forth with, that was dependent upon its length. So this then should swing differently in terms of the time it takes if it's a different length, which if you think about it, if the period's different, so is the frequency then. All right, so here comes our big connection then. The frequency should be different for this one, and then I should hear something different that depends upon frequency. So here we go. All right, so assuming I didn't really strike it that much harder or bring it too much closer to the microphone, hopefully what you heard is a note that got a little higher. All right, if you think about how high something sounds, it's kind of like opera singers, I guess, is a good example. Like they can get really high with their notes. This is what we call pitch. So, I mean, that movie, I'm sure you guys are aware, Pitch Perfect. It's basically making sure they're in the right key. All right, they want to have the right pitch. So, that's the big idea today. But I want to take it a step further. What's kind of cool is if we did the lab, if you guys see in the bottom right of my iPad screen right now, TW Recorder, it's an app where we can actually record any sound and then analyze it in terms of a wave. All right, so I'm going to grab one of those tuning forks. I'll do the one I finished off with. And I'm going to record it, and then, of course, the sound wave should show up on the screen. So here we go. All right, so there's the sound, which you guys may have seen this with computers before when you're watching like a movie. Like, sure, it'll just kind of show this blur that kind of has a different shape. Doesn't really look like a wave right now, but here's what's nice about this app. I'm going to pinch zoom, and then all of a sudden, when I get in enough, you guys are going to see that wave shape we've been talking about. The only downside to this is when these tuning forks do get kind of banged against hard objects, the makeup of them isn't what they should be. So you see how the wave isn't perfect. That will happen the more the material gets broken down. But for our purpose, it's pretty good. What you will see, though, above the graph is you'll see times, and in the very top right, you'll see a selection length time. Well, right now it's 0 because I haven't selected anything, but if I tap on the screen and then drag this, I can get a selection time, which is still tiny, 0.025 seconds, but it is a time I can work with. So what I'm going to do is I'm going to actually try to get 10 cycles. So let me count them out. I kind of start at this first peak. So the second peak would then be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I actually need to, I need to back up just a tad. So let me double check this again because it is starting at equilibrium actually. So I want to skip the first peak. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that is 10 cycles. You can pause it and check me if you want and then yell at me if it's wrong. But if I look at the top right now, it then says the time of 10 cycles is 0.023 seconds. Well, we did this in the pendulum lab. I can actually then get the time of one cycle, the period, by dividing that by 10, which is just then 0.0023 seconds. Why is this all relevant? Remember the relationship between period and frequency is the inverse. So if I do 1 divided by 0.0023, the time of one cycle, I actually get about 435 if I'm rounding up. That's the frequency, so 435 hertz. If I look at the actual tuning fork in the kit, it is the key of A, and it's supposed to be at about 425. So it's not perfect. I'm about 10 hertz off, but it's pretty good considering it's probably been banged against a few hard objects. All right, so that's kind of the nice thing is that we can actually get these very clean tones like these tuning forks, and then when we analyze them, they look exactly like the sound waves we've been talking about. All right, if I were to, of course, grab a different tuning fork, I could do this exact same thing, but I would bet, of course, the time wouldn't be the same because they're different frequencies. But they should still, of course, show nice standing waves. Another fun thing I'll at least show you guys right now is that not every sound that you hear is going to be as clean as what you see on the screen right now. My voice, for instance, it's not a very pure tone, so I'm going to record it real quick. All right, so if I'm talking right now, just like I were to you guys, at first you might think, well, maybe we can zoom in on this and it'll look really pretty. Well, you might start to see patterns, and you can see clearly how it's changing at certain locations. At the beginning there, that actually does look like a pretty decent wave. It's kind of my Eeyore, really low tone, really low frequency, so that's not too bad. But then, of course, when I make different sounds based on my speech, you can see the wave patterns definitely got to change in terms of shape, frequency, wavelength, amplitude possibly too, although we'll get to what that is. I don't really vary that too much. But kind of daily noises are going to be more complex than what you guys saw with the tuning fork, okay? All right. Anyway, with this, though, if you guys want to read up in the textbook about it real quick, too, that would be awesome. I'm not going to assign any homework tonight, but feel free to reach out to me in the office hours today. They are from 2 to 2:30 for our class. And if you just want any clarification or kind of want to take this in depth a little bit more, that's definitely what I'm there for, okay? Just for fun, too, if you actually want to download the TW recorder, I can't remember if it still looks like this icon or if they updated it, but it might be fun for you guys to actually download that and then kind of mess around with some noises. Like you could actually just take random objects in your house and just kind of make a noise with them, for instance, like hitting a glass filled with water, which is something we'll get to in terms of standing waves with sound, but I think you guys have seen stuff like that. So have a little fun. Hopefully you guys had a good weekend. If I don't see you in the office hours, I will see you guys tomorrow on Tuesday, okay? Take care.